Hi, this is the second part of the Further Maths Core 1. We're still looking towards 7B. This is the second video. I haven't decided yet. I might put them all into one. So example 6 describes a rotation 180 degrees about 0, 0. So let's put our unit square on, then rotate it. Remember, separate colours for each side. So this is example 6. So there's my unit square. I'm going to rotate it 180 degrees about 0.0. Now it doesn't give us a direction. Well, 180 doesn't actually matter. Remember, the positive direction is always anti-clockwise from the x. But as I say, it doesn't actually matter for 180 degrees. So the red line will end up there. The blue line will end up pointing downwards. There it is. Now, if you think about the last example, the squares look the same, but crucially the sides map differently. It was a reflection, this is a rotation, and I'll just indicate that I started with A, I finished with A dash, object and image. Well, I can write down the matrix just by looking at where red ends up and where blue ends up. So P is 1, 0 goes to, 1, 0 goes to minus 1, 0, and 0, 1 goes to 0, minus 1. So that's the matrix which represents a rotation of 180 degrees about 0, 0. Now, if I want to show that y equals 3x is invariant, so y equals 3x, the line y equals 3x maps to itself, to show that, then I apply my transformation matrix to a general point on that line. You might want to pause this, rewind it, have a think about it, get your head around it, but of course this is x, y. This is any point on the line y equals 3x. And if we multiply this out, minus x, 0 times 3x gives me minus x. 0 times x minus 3x gives me minus 3x. In my product, it's still true that the y-coordinate is 3 times the x-coordinate. So y equals 3x holds for the image. So if you like, I input y equals 3x and I got out y equals 3x. Now, this doesn't mean that every point on y equals 3x stays the same. It means that the line y equals 3x, if you like, the locus of all the points, maps to itself. So if I pick a point on y equals 3x, it wouldn't stay there, it would go down there. But join all those points together and I get the line y equals 3x. Invariant points and invariant lines is actually quite a big deal and not covered very much in this book. So I'm not going to go into great detail about invariant points and invariant lines. Now, I'm not going to do example 7 yet. I'm just going to talk about rotations generally. Here is my unit square again. I'm going to draw it quite big this time. Oops. Okay, so here's my unit square again. I'm going to rotate it about the x-axis, but I'm not going to do it a multiple of 90 degrees or even a factor of 90 degrees. I'm just going to do it theta. make it as square as I can. That'll do me. So my red side is now there. My blue side now goes there. And that angle there is theta. Remember, my positive angle is anti-clockwise from the horizontal axis. What I want is the coordinate of that point and the coordinate of that point. Or the coordinates, sorry, not the coordinate. Well, if we just consider this triangle. Consider this triangle. It's a right angled triangle. Theta. I know that that side length is 1. Of course, that's then my opposite side, and opposite over hypotenuse is sine. So this is sine theta. This is my adjacent side, and adjacent over hypotenuse is cos. So this side is cos theta. So my 1, 0 has mapped to cos theta sine theta. So 1, 0, 0, 1 maps to cos theta sine theta. And this point here, well, what do I know? If I think about what I know, let's make my right angled triangle. That angle there is theta. Alternate angles means that angle there is theta. I'll save you the bother of working it out. My horizontal side here is minus sine theta. My vertical is cos theta. Now you don't need to remember this. You're given this in the formula booklet. I think I've got the formula booklet open somewhere. You can just about see there. I'll drag it into the window. In the formula booklet, we're given this matrix, so we don't need to remember it. But I wanted to show you how we got it. So bearing in mind that we're given this matrix represents a positive, if you like, anti-clockwise rotation of theta about 0, 0. Okay, example 7. There we go. Example 7 gives me minus root 2 over 2, minus root 2 over 2, root 2 over 2, and minus root 2 over 2. Now I'm looking at this and thinking, oh, hang on a minute, those look like exact trig values. It is a rotation. The question actually tells me that it's a rotation. And using the matrix that we're given, the one that we've just derived, I can say cos theta, so cos theta's top left, sine theta's bottom left. So I can write cos theta equals minus root 2 over 2, sine theta equals root 2 over 2. Working in degrees doesn't actually matter, but my calculator happens to be in degrees, and I know that these are nice numbers, so it's got to be a nice value. If I do inverse cos of minus root 2 over 2, gives me theta is 135 degrees. Remember, on a cos graph, there'll be two solutions. One of them is 135. The other one comes from 360 minus 135. So let's do that. So theta is 135 or 225. If I solve sine theta equals root 2 over 2, inverse sine of root 2 over 2, 45 degrees. Remember, with a sine graph, there's my 45, so I take it away from 180. Well, let's take away 45, 135. Oh, good. So I have got a value of theta that agrees between the two. So theta must be 135. Theta equals 135. This then is a anti-clockwise rotation about 0, 0 of 135 degrees. Divided by 118 times by pi, 3/4 pi radians. So we're given the matrix that defines the rotation. We just need to solve for theta, find the angle that agrees. Done. Part B wants us to apply the matrix to 4 points. We could easily do that. 1, 0, 2, 0, 2, 1, and 1, 1. And the calculator will tell us the answer. Let me find it. It's on the next page. Minus √2 over 2. √2 over 2, just fit that on the bottom. 2, 0 goes to minus √2 over 2. No, it doesn't. It goes to minus √2 and then √2. 2, 1 goes to minus 3 √2 over 2. √2 over 2. 1, 1 goes to minus √2, 0. Just managed to fit that on the page there. Just be careful because it's asking me for coordinates, so I'll need to write out these individual pairs as coordinates. So 1, 0 maps to minus √2 over 2. √2 over 2, that's just from the first pair, etc, etc, etc. 2, 0 maps to minus √2, 2, 1 maps to minus 3 √2 over 2, √2 over 2, and 1, 1 maps to minus √2, 0. Okay, I think that's everything we need for 7B. Give it a go. Let me know if you need anything. See you next time.